Hello, and welcome to Introduction to Equilibrium. We're going to specifically focus right now on chemical equilibrium, which is when you actually have a chemical change that can be reversed. So if we put some sulfur dioxide, SO2, and oxygen, O2, into a container, they can actually react with one another. So we can have a reaction occur with SO2 and O2. In order for this to happen, the O2s do have to split, and then you can have these guys kind of go and end up joining themselves to an SO2, in which case they will form SO3, sulfur trioxide. So in other words, two SO2s plus an O2 make two SO3s. This is all balanced, nicely written for you so you can see this synthesis reaction. And I depicted this here in pictures. You don't really need to draw this out necessarily, but I did think it would be helpful for you to see. So again, what's actually happening is this guy can split. One of them goes to each of those places. And then you end up with two SO3s. Now, here's the deal with SO3. SO3 under the right conditions can actually decompose back to SO2 and O2. So this is what's called a reversible reaction. So some of these oxygens can come off and form a new little O2 right here and leave behind those other two SO2s. So this is a reversible chemical reaction. In a reversible chemical reaction, reactants can form products which can then go back and form the reactants again. So our forward reaction here was that reaction of SO2 and O2 making SO3. What would be considered a reverse reaction is our two SO3s breaking back down into SO2 and O2. Now, we don't want to have to always write both of these things, so we have a way in chemistry of writing a reversible reaction. And really, you can write it in either order. I'm just going to go with the way I wrote it in the first one. And then we do a special little thing with our arrow, where we draw two arrows like this. If you're typing this on a computer, there's actually an arrow that looks like this. That's also acceptable as well. So whatever's kind of easiest for you, and you can actually draw it that way if you like. But that double arrow is typically what chemists use. Now, in reality, we don't really usually just have SO2 and O2, or just SO3. We usually have a combination of both of those things. So if we put SO2 and O2 in initially, they're going to start to form SO3, but at the same time, SO3 might decompose back into SO2 and O2. So in reality, at equilibrium in our container, we're actually going to have O2s, SO3s, and SO2s. We're going to have all of those things present at one time. What's kind of difficult to see in this particular picture is that we actually have a very dynamic system here. So this SO2 right here might have been an SO3 just a minute ago, and it might quickly become an SO3 again, and then change back even to an SO2. So we actually have two competing chemical processes going on inside of this container. So what it actually means to be at chemical equilibrium is that we have two processes that are kind of the opposite of each other happening at the same time. And the rate of those two processes are equal. So in a chemical equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So these two opposing processes happen at the same time at the same rate. Now, this does have an effect on concentration. So if we had started like we talked about in the beginning with SO2 and O2, so this red line right here is representing the starting amount of SO2. This starting line right here is representing the starting amount of O2. And then we started with none of our products. So we had zero SO3 at this point. So as SO2 and O2 began to react, they began to form SO3. So as the reaction between SO2 and O2 occurs, this is going to decrease their concentrations. they're forming SO3, so we can see that the SO3 is increasing. What is really important on this graph is what happens right about minute 4. And I don't know why there's that little blurb there, but what really occurs that we care about is the fact that from minute 4 on, our concentrations remain constant. So what this actually means is every time an SO2 and an O2 form an SO3, simultaneously a different SO3 breaks back down into SO2 and O2. So if we started with SO2 and O2 only, our forward reaction is going to occur and form SO3. That is simultaneously decomposing. To make our SO2 and O2. So when we have reached equilibrium, those things are happening at the same rate. And what this actually causes is a situation where if we look at our concentrations, they will remain constant at a certain time. So when we reach minute 4, we have a 2 molar concentration of SO2. Our concentration of O2 is about 1 molar. And our concentration of SO3 is 8 molar. Something that can be a little bit confusing for students is identifying in this graph where the important thing happens. The important thing happens where concentrations become constant. The fact that these intersect with one another isn't actually all that important. Now, if we did the reverse thing, so if we started with the reverse reaction and we put a bunch of SO3 in the container, but we had conditions the same. What we're actually going to have occur is we're actually going to reach the same equilibrium, just with the opposite starting stuff. So what we can see here is we started with our reverse reaction happening, which is the SO3 forming SO2 and O2. And as that's occurring, you see that SO3's concentration decreases and SO2 and O2's concentrations increase. What you'll notice is when you look at this graph, they become flat. So you see that again. They do not intersect. That's okay. So they just didn't happen to end up with equilibrium concentrations. They require them to intersect with one another. But what you will notice is if you look at your equilibrium constants, we again have 2 molar concentration of SO2, 1 of oxygen, and 8 molar of SO3. What is actually happening when we are at equilibrium is these reactions are all still occurring. They're happening at a very balanced rate, an equal rate actually, that keeps those concentrations constant. So these reactions have not stopped. They are both continuing to occur at the exact same time. And because of that, we actually end up with what we call a constant concentration. The concentrations are not equal to one another, they are constant. And this leads to a little saying I like to use: at equilibrium, concentrations are constant. We have to remember that concentrations are not equal. So I'll give you a nice mnemonic device that will help you with questions talking about equilibrium rates versus equilibrium concentrations. Oops, I did not want to do that yet. So the little saying that I like to use, I apologize, we're going to get shifting tomorrow, is this: at equilibrium, concentrations are constant. Rates are equal. So at equilibrium, concentrations are constant. See what I'm doing there? Rates are equal. Concentrations are not equal. You could have a system maybe where they are, but that's not definitionally true. But rates do have to be equal. So what this actually means is if we kind of flip back to the visual, where we can see both possible reactions. Every time we have a couple of these get together, I should actually circle 3 of them to make it more correct for the reaction. Every time 3 of these become one of those at the exact same time, two of these are breaking back down into these things right here. So we have two opposing processes happening at the exact same rate. Because they happen at the exact same rate, they create equal concentration, or they create constant concentrations.